Hello and welcome to this little lesson on momentum for GCSE physics. Now, this is a topic that many students struggle with, but it honestly is as hard or as easy as you make it. So do approach it with an open mind and let's see where we end up. So let's start off with what momentum really is. It's essentially a property of matter. And I know that sounds a bit confusing, so I want you to imagine momentum as a rugby player. We've all seen rugby, some of us will have played it in school. And a rugby player carrying the ball just wants to get to the other side as quickly as possible and with as much force as possible. So imagine a big rugby player running down the field. Now, this rugby player requires a lot of force to stop. If you want to tackle this rugby player, you're going to have to hit them very hard and with a lot of speed. So essentially, it takes a lot of force to change someone's momentum or something's momentum. Now, momentum is a vector quantity. What that means is it doesn't just have size, it also has direction. That's because of what it's made up of. So momentum is the product of velocity and mass. So mass is the magnitude, the size, and velocity is speed in a given direction, as you already know from previous lectures. So velocity is speed in a given direction. Remember that. The given direction part is what makes momentum a vector because it also has direction. So, for example, you can have negative momentum in an equation where you're assuming that movement to the right is positive and movement to the left is negative. So negative momentum may be possible, and that will become relevant later. Now, force has an interesting relationship with momentum that we do need to consider. So, like I said earlier, it takes force, and sometimes a lot of it, to change momentum. Now, this can be put as a little equation where change in momentum is equal to force times time. What that means is the more force you apply, and the greater the time over which you apply this force, the greater the change in momentum will be. And that makes sense, right? Because if this rugby player is thundering down the pitch, to stop them or to change their momentum and tackle them, you're going to have to use a lot of force. And if you can exert this force for a greater amount of time, you're going to be able to push against their momentum more easily. So that's why when tackling someone in rugby, it's good to take a running start. You don't just want to be standing there waiting for the person to hit you because you'll have very little momentum compared to them and they'll just knock you out of the way. Whereas if you're running towards them yourself, you're building your momentum against theirs. And if you can exert that strength and that momentum for a greater amount of time, you can eventually overcome their momentum and change it to a negative direction. So if forward is positive and you want to move them backwards, assuming backwards is negative, with enough force over enough time, you can change their momentum to favor yourself in this rugby game. Now, remember, force is equal to mass times acceleration. So they may give you a question where, for example, they're asking you to calculate momentum, but they've only given you mass and acceleration. Now, the way you're going to do this is you're going to calculate the force, and then you can use force times time, provided obviously they've given you time to calculate momentum. They may be even more cheeky, and instead of giving you acceleration, they may give you initial and final velocities and time, in which case you're going to have to use that equation which you may remember. A is equal to v minus u over t. So A, acceleration, is equal to final velocity minus initial velocity over time. That will give you the acceleration, and because you've got time already, you can then calculate the force, and using the force and the time, calculate the momentum and the change in momentum. So you have to think on the spot with these things. They're often going to hit you with quite difficult problems which require multiple equations, because as you remember just from the previous slides, the equation for momentum is very easy. P is equal to mv, mass times velocity. It's rare that they're going to give you a question that easy unless it's only a mark or two. Now, the law of conservation of momentum. Now, this can be a bit confusing to some students, but I once again encourage you to just take an open-minded approach to it and forget how difficult it can be, and all of a sudden it will become nice and easy. The key thing to remember is, like energy, momentum cannot be created or destroyed, because remember, pretty much everything is energy, right? You can't create or destroy energy, therefore you cannot create or destroy momentum. Now, in a closed system, what I mean by a closed system is one that, well, it's closed. It doesn't have external forces or energies acting upon it. In reality, we have very few closed systems. That's because, for example, if two cars crash into each other, the momentum is going to dissipate into the air because it is a form of energy, really, right? In energy, because you can't really create or destroy it, it spreads out. That's how we get rid of energy. Otherwise, we would have energy everywhere. So it dissipates just like momentum. However, for the purpose of the calculations that we're going to be doing, we're going to assume that the system is closed. This means that the energy and the momentum has nowhere to go, and therefore it will be conserved. So the total momentum before an event will be equal to the total momentum after the event. For example, if two cars crash into each other and the one car is moving to the right with a momentum of, let's say, 100, and the other car is still, and as a result, it has zero momentum because remember the velocity is zero because it's not moving in any given direction. That means the total momentum before the event must be 100. Now, because it has to be equal after the event, the total momentum after the event must also be 100. This is useful because, for example, if you've got the mass and velocity, let's say, in fact, not the mass, let's say you've got the velocity of the moving car and you have the momentum of the moving car and you need to calculate its mass. And also, well, you can do that using momentum divided by velocity. Now, let's assume you also want to calculate how far the second car, the one that's being hit, moves in any given direction. And you have its mass, for example. The way you're going to do that is using the law of conservation of momentum. So you know the total momentum after the event must also be 100. So you can divide that total momentum by the mass of the second car to calculate its velocity. And once you've done that, you know how fast that car, the second car, the one that's being hit, is going to move in any given direction. Now, this has lots of real life applications. We can use this when we're calculating, the effects of road traffic accidents to see how someone might be injured if they were hit by a car. Because replace the car with a passenger or a pedestrian rather, who's being hit by a car, you need to be able to calculate what their momentum and velocity is so you can figure out how much damage they may take. And that will allow you to treat them accordingly in medicine, for example. So remember, the total momentum before an event must be equal to the total momentum after. And think on your feet. So remember to use the equation in all of its different forms. F is equal to ma, a is equal to v minus u over t. And just bear in mind what you're trying to calculate. Write down all the equations in one go if you have to, and then simply substitute in the values that you have been given, and gradually work your way to the final equation of P is equal to mv. And that's all really. There's not much more to momentum. Next time we're going to go over some practice problems and see how you guys get on. So I encourage you to go over this lesson a couple of times just to get your head wrapped around it. And the next time I will see you with some problem solving skills. All right. Thank you.